Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. Problem 127. Water at 20 degrees Celsius of viscosity 0.001 Pascal second flows in a 750 millimeter diameter pipe. The center line velocity is 3.75 meters per second, and at 75 mm from the center line of the pipe, the velocity is 3.6 meters per second. So compute the flow rate. Letter B, the head loss in a distance 200 meters, and letter C, the friction velocity. So for our solution, let's begin with the formula for the velocity at distance r from the center line given by v sub r equals v sub c minus 5.756 square root of quantity tau sub o over density log of quantity rho over rho minus r, where our discharge is pi over 4 diameter squared times v, area of circle times v. This is a working equation. Then we need the mean velocity v. So as I said, v sub r equals v sub c minus 5.756 square root of tau sub o over density log of quantity r sub o over r sub o minus r, where r sub o is the radius of the pipe, which is 375 mm, and r is 75 mm. Then square root of tau sub o over rho is also, which is the denoted by v sub asterisk, which is friction velocity or shear velocity. It is also equal to mean velocity of flow square root of f over 8. So replacing that by v square root of f over 8, so v sub r is 3.6 equals 3.75 minus 5.756 v square root of f over 8 log of 375 over 375 minus 75. So simplifying this term, transpose to the left, then 3.75 minus 3.6 is 0.15. So 0.1972 to v square root of f equals 0.15. So v square root of f is equal to 0.76057. Then the Reynolds number. Center line velocity is v quantity 1 plus 1.326 square root of f. If we distribute this, then v sub c is 3.75. Then we have v plus 1.326 times v square root of f given by this value. So 3.75 equals v plus 1.326 times 0.76057. From here, we can solve for v, 2.7415 meters per second. Then we can now compute the discharge, pi over 4 times 0.75 square times 2.7415. So the discharge is equal to 1.211 cubic meters per second. Then the head loss in the distance of 200 meters, knowing the mean velocity of flow, substitute in this formula here, we can now compute F. So 2.7415, head loss is FL over D, velocity head. Then F is from here, 2.7415 equals square root of f equals 0.76057, square both sides, then we can solve for f. F is equal to 0.07697. Then substitute into the Darcy-Weisbach formula for head loss. HF equals 0.07697, length 200 over diameter 0.75, velocity head 2.7415 square over 19.62. So the head loss in the distance of 200 meters is equal to 7.863 meters. Then finally, the friction velocity. It is square root of tau sub o over rho, or v square root of f over 8. So let's use these two formulas to verify that the results are the same. So v asterisk square root of tau sub o over rho, it is v square root of f over 8, where tau sub o is specific weight head loss diameter over 4L. So specific weight is 9,810 newtons per cubic meter. The head loss is 7.863, diameter 0.75 over 4 times 200. So maximum shear stress or tau sub O is 72.315 pascals. Then we substitute into this equation both these equations. So V sub A series is square root of 72.315 over 1000 or 2.7415 square root of 0.07697 over 8. So the friction velocity is the same for these two formulas, 0.2689 meter per second. Problem 128, a liquid of specific weight 9.120 kilonewtons per cubic meter and kinematic viscosity of 0.0005 square meter per second flows through a 100 millimeter diameter pipe. The friction factor is 0.08 and the flow is known to be laminar. Determine part A, the flow rate, the maximum shear stress, and part C, the center line velocity. So for our solution, discharge or flow rate is pi over 4 diameter square times mean velocity. So we need to know the mean velocity of flow. Then because friction factor is 0.08 and it is known to be laminar, friction factor for laminar flow is 64 over Reynolds number. And from here, we can compute the Reynolds number. So 0.08 equals 64 over Reynolds number. So that means Reynolds number is 800, which is less than 2000. So that shows or proves that the flow is really laminar. Then Reynolds number is also equal to the diameter times mean velocity, diameter 0.1 meter, mean velocity unknown, divided by kinematic viscosity. So from there, we can compute the mean velocity. So Reynolds number, diameter mean velocity over kinematic viscosity, 800 is equal to 0.1 times mean velocity of flow over 0.0005. So the mean velocity of flow is equal to 4 meters per second. Then we can now compute the discharge, pi over 4 times diameter 0.1 square times mean velocity of flow 4. So Q is equal to 0.03142 cubic meter per second. Then the maximum shear stress, is either specific weight head loss diameter over 4L or friction factor density velocity square over 8. So we will use these two formulas in computing for the maximum shear stress or tau sub O. First, this one, but the head loss is not yet known. So we use the Darcy-Weisbach formula, FL over D velocity head. So FL over D velocity head, since friction factor is 64 over RE, 0.08, and length is, you just consider 1 meter, and diameter is 0.1, then the velocity is 4. So head loss over L is equal to 0.08 over 0.1, friction factor over diameter, then velocity at 4 square over 19.62. So head loss over length is equal to 640 over 981. Then the tau sub O therefore is specific weight, then head loss over length, which is 640 over 981, then diameter over 4.1 over 4. Likewise, it is also friction factor times 9120 over 9.81, 9120 over 9.81, head loss over length, this is 0.08 friction factor, then density is specific weight 9120 newtons per cubic meter over 9.81 meters per second square, then velocity square over 8. So both formulas give the same results. answers of tau sub O in pascals, 148.7 pascals. Then finally, the centerline velocity. The centerline velocity for laminar flow is twice the mean velocity. Therefore, the centerline velocity is just 2 times 4, and therefore it is 8 meters per second. So that's it for this problem.